This is a presentation of the Bitcoin trading bot designed for the Capstone Project for the Oregon State University Computer Science program. We'll hear from myself as well as from team members Derek Lyon and Prasanna Thapa. We used neural networks to predict Bitcoin values and automate trades. We used TensorFlow's time series documentation to train models on historical Bitcoin datasets collected from the Binance API. The final Python 3 bot downloads the training data in real time, trains the model, and either buys, sells, or holds every 5 minutes based on the predicted price. Neural networks are well suited in time series forecasting. The historical Bitcoin dataset retrieved from the Binance API is structured in a time series format.
So there are three distinct parts to this project. The black box, where the model is trained, the red box, where the model makes prediction decisions, and the third, which is the interface of the model that gathers the data and executes paper trades. For this third part, we use the Binance public API. The user has to create a Binance account with an API and secret and store it locally in a config file in order to be able to trade. Based on the decisions of the first two parts of the project, this third part will execute trades and show trade visualizations like efficiency and generated alpha.
To train the recurrent neural networks, the TensorFlow documentation recommends the use of time windows. We provided the RNN with an input sequence from the dataset, which in our case was the value of Bitcoin every minute for the past 60 minutes. We also included the subsequent values for the next 5 time steps as labels. The loss, which tells you how accurate your network is computed during training by comparing the outputs the model predicts against the expected output labels. To measure the performance of the models, the RNN is also run against a validation dataset to calculate the validation loss. This is used to determine how well the model works with the data and to prevent overfitting. Here we have a sample 2-hour window of the normalized Bitcoin price along with the 3 labels, which again are the actual values at those time steps, and the 3 predictions from the model for those time steps.
After a suitable model is selected and trained, an automation routine is used to achieve a practical application of our model. The flowchart on the right shows the logic used by our automation script. First, our saved neural network model is loaded and recent price data is queried from the selected crypto coin exchange. This data is fed into the model to get a prediction of where the price will be headed. At this point, we must apply a trading strategy to decide when to buy or sell and how much to trade. There are many viable trading strategies that can be applied. The easiest strategy is simply executing a buy or a sell based on if the last data point is above or below the prediction. In the diagram, a threshold strategy is applied to reduce trading sensitivity. Here, the model only executes a trade if the prediction is above or below 1 standard deviation from the mean of recent price data. This attempts to limit trading decisions to only statistically significant predictions. Here is a recording of our trading script in action. To ensure it's trained to the most recent data, the script launches a pre-processed training procedure defined in our training.py file. Once training has completed, it will immediately load the trained model from storage and query the Binance exchange for the last 60 minutes of price data. This data is normalized and fed into our model to get a prediction of what the Bitcoin to US dollar price will be for the next 5 minutes. At the same time, the routine also calculates the standard deviation of the last 3 hours of price data. The prediction is then denormalized and a trading decision is made. In this case, the predicted price is below 1 standard deviation of recent trading data, triggering a sell order. Now, a 5-minute timer will start until the next prediction cycle begins. TensorFlow's documentation provides a tutorial for time series forecasting using neural networks. I worked to create a modified window generator class derived from the documentation to allow for models to be created in an object-oriented fashion. This choice was deliberate to allow for rapid prototyping of various model architectures during development. I was also responsible for implementing the trading bot script and integrating components such as the training routine to be compatible with the bot script for regular retrainings. I implemented the LSTM recurrent neural network model. Lastly, I explored optimization routines to enable dynamic model restructuring when market conditions change beyond the capability of the initial model structure.
I reworked TensorFlow implementations by data scientists Greg Hogg and Srinivas Bhattiprolu that were originally designed to work with weather and stock market data, respectively, so that they could work with the Bitcoin data. One of the outcomes of that exploration was a document detailing the time window approach. I also set up a remote server for the team so that the completed bot could be run in an environment without any downtime. I also ran the GRU variant of the trading bot script to collect data so we could compare performance against the LSTM and convolutional network models.
I was responsible for creating the interface between the application and the Binance API that executes the paper trades. Calls could be made to this interface in order to execute any of the required trades for any cryptocurrency. I used an iterative method in order to implement different models used for the training. I started with a baseline prediction model. Then I went on to a linear prediction model, a dense neural network model, and then finally a 1D convolutional network. I also researched the statistical approaches to calculate the alpha generated and the correlation between the price of Bitcoin and the alpha generated. In my project, I used the alpha generated to feed back into the model such that the training takes place when a majority of the last 5 trades generate negative alpha. And therefore, whenever the bot is performing poorly, we tell it to retrain itself. So the goal of the project was to train an AI bot that could trade cryptocurrency. To this end, we succeeded. Further, the reason to create a project of this type is to generate profit, or more appropriately, alpha. Alpha is the comparative measure between the return from the AI model and a benchmark. The formula shown in the screen calculates alpha based on the benchmark of holding assets long-term and not trading. Positive alpha means the AI model outperformed the benchmark, while negative alpha means it performed worse. Further, the data of alpha generated could be fed back into the model to help improve the model's performance as well. Now, since each teammate created different models, the alpha generated will be different for each of their models. Here we showcase the alpha generated by these models during the same time frame. At the top right, we have the one-dimensional convolutional neural network. In the bottom right, we show the alpha generated using a gated recurrent unit, GRU, and the bottom left is the alpha generated using the long short-term memory, RNN. We expect that each model will perform better under differing market circumstances, and that this is just a particular circumstance that favors one model over the other.
An important consideration for our project is the period of relevancy of our chosen models and how they respond to changing market conditions. An LSTM model was optimized manually and allowed to run for 4 days. We observed somewhat reasonable performance for several days. However, despite retraining hourly, it was observed that metrics like validation loss began to perform continually worse, and performance subsequently suffered. One possible explanation is that the optimization was performed manually during the market conditions of that time. As market conditions change, the model architecture itself may no longer be suitable. This highlights the need for a more scalable approach to optimization. As we conclude this project, let's discuss areas of opportunities for further improvement. To address the optimization scalability problem, we created an optimization routine that compiles 3 different model complexities over a range of important training parameters, totaling the creation of 192 distinct models. Using the TensorBoard visualization tool, we were able to identify which models had the best validation loss and mean squared error performance. While computationally intensive, this routine could be integrated with the current training bot to identify top performing models and dynamically switch to the best model in current market conditions. From there, we would implement a hosting platform and create a graphical interface to create a user-friendly and marketable product. On behalf of the group, we'd like to thank you for the opportunity to share our findings, and we'll be happy to answer any questions you may have.